I will continue with Module 4, Practice Test. 14 questions. And they're asking us to simplify this radical. So the radicand might be familiar to you. To me, it looks like a perfect square trinomial that when we factor it, will factor into a binomial square. Let's see if it does that. So this will be 4x minus 3. That is, we took the square root of that and got 4x square root of that. Now if we square this, we get that. And if we square this, we get that. And if we multiply these two together, we get a negative 12, double it, negative 24. So that looks pretty good. Now the thing to remember is when we put our answer into the system, we have to indicate that it could have been a negative value, so we use the square root sign of this. Now remember, our index number is 2, and the exponent of this is 2, so 2 divided by 2 is 1. So that's a pretty good hint. This one is pretty straightforward. We're taking the fourth root of something, and this is a perfect fourth power of something, and anything divisible by 4 as far as the exponent goes is also a perfect fourth, and they're saying it wasn't a negative quantity raised, so you don't have to worry about the absolute signs. Now whenever we have an even index number, we can't have a negative value under the radical sign and have it be a real number. So with an even index number, the technique for finding the domain is just to take the radicand and equal it to 0. Now, again, I don't want to solve it particularly, but let's say from this you said that x equals 3. That's not the answer here. You have to find out what x equals. So its x would have to be greater or equal to 3. That would be the domain elements. So how would I write this in interval notation? Well, I'd use a bracket. I'd put a 3 here, comma, and to positive infinity. So that would be the way to write this answer in interval notation once you find what x is. Well, the strategy behind this is to convert this from its fractional exponential power into its radical form. And the general recipe, and of course I've changed it, is this then becomes the radicand. The denominator of our fraction becomes the index number, and then this is to the first power, which is assumed. So again, you have to do this one. This is an example of how to do it. Now for something like this, and it's a little hard to read there, but I think this is what they're referring to. When we are raising a power to a power, we multiply the exponents. So this will become 5. And then here we can cancel out a little bit. 2 goes into there 3 times. 2 goes into there once. So we now have in the numerator 11 over 15. Type exponential notation with rational exponents. Okay. So the thing is, it's the technique here, and I guess I've done this one for you, but yours will probably have different numbers, but this is the technique. You can cross-cancel, and then you multiply and simplify. Okay, so they want us to simplify this. Now remember, in the notch, when there is no index number, there's a 2 there. And this is the radical way of expressing this. Well, to convert this to a fractional exponent, we take our radicand, and we take the index number as our denominator of the exponent, and the actual exponent of the radicand goes there. So this then becomes AB to the 10th power. And if we wanted to simplify, I don't know if they want us to leave it like this or to write it this way: A to the 10th, B to the 10th. Both of these are correct. Again, I went a little far on this one. Now here they want to simplify this by factoring. And the technique we'll show in class is you make 2 radical signs, and under one radical signs you're going to put any perfect fifth factor of 96. And you might say, I don't know how to do that. Well, I'm showing over here the prime factorization of 96. And I have 1, 2, 3, 4, 5. 2 to the 5th power is 32. And then there's a 3 left over. That's not a perfect fifth. Then I look at my x to the 12th. Well, any fifth multiple of 5 in there, x to the 10th, would be a perfect fifth. And what's left over is x to the 2nd. And then y to the 15th is a perfect fifth, y to the 15th. So now what you'll do is take the 5th root of these, and then this is what's left over, and that's how you put your answer in there. And we've done some like this, or we'll do some in class. Now as we go over this in class, there are different ways to do it, but we know we can multiply the radicands in the normal way. 3 times 6 is 18. X to the 7th times x to the 2nd is x to the 9th. And now we can use that technique of using 2 radical signs. Is there a perfect square factor in 18? Yes, a 9. And what's left over is a 2. Is there a perfect square in x to the 9th? Again, it would be an even power, x to the 8th, and then an x. So now you take the square root of this, and this is what's left over, and you put that in your answer column. Again, there are other ways to do this, but the square root of 400 is 20, so I took that out, and I left this here. And I then get 20 over 2, which reduces to 10. The square root of xy over 2. That would be one way to do it. Let me try another way. Again, I'm not sure there's just one way to do it. Another way is what I have here. That is putting the radicals under a common radical sign and then canceling the 2 into the 400, which gives you 200. But then your 1 over 2 is still out there. Now taking this 200 and dividing it into 100, which is a perfect square, times 2xy, then the square root of 100 is 10. 10 over 2, that's going to be 5 now. The square root of 2xy. I think I'll go with this answer. Let me say that this answer and this answer are equivalent. That's the word I was looking for. Okay. The rationale for rationalizing the denominator, see, good use of the word, is to multiply your denominator by something that will make it a rational number. Right now it's irrational. So I want this denominator eventually, when I take the third root of it, to become a rational number 5c. So what do I multiply it by? Well, I have 1 5, so 5 times 5, or 25, will make this 125, which is a perfect cube. And then this is c to the first, so I have to multiply it by c to the second. So now this becomes c to the third, and the cube root of c to the third is c. Now, I'm allowed to multiply anything by 1, and the form of 1 I'm using is 25c squared, the cube root of that over the cube root of that. So this is just a 1. But now I have to multiply my numerator, and I get the cube root of 3 times 25, which is now 75, a c to the second. So I have rationalized my denominator. Now when you get to do these, I've seen enough of the practice tests that the numbers change. But this is the pattern that you will need to follow. Now we're dealing with radical equations, and the tool we dig up is to get rid of the radical sign by taking it to the index number power, which is a 2 there. So we square both sides. So when we square this, we get 49, square that, and then squaring this, we just get the radicand, and that equals x squared. Now we put that in standard form, x squared minus 49x. Factor out the x. In the next chapter, we're going to get some other ways to solve quadratic equations. And this equals 0. So we're going to get two answers here back from our work in Chapter 1 and Chapter 2. And those would be our answers. Now, generally, you should check them to see that both are going to work, and both do work here. All right, this one's a little tricky, so I'll work it through with you. Remember that the square root of -1 equals I for our imaginary numbers. So now the square root of a -64, we take out the I, which is the square root of -1, and we get 64. And following this down, it's just square root of 64 is 8, 8i. That's this part here. Now here I'm taking out the square root of -1, and then I'm left with 50, and then I'm dividing the 50 into a perfect square, 25 times 2. So square root of 25 is 5, so that gives me 5i, the square root of 2. Now when we write this, they want us to write it in this form. So we have to have the I at the end here. So this term has an I, this term has an I. We factor out the I. A lot of students get this incorrect because they fail to put it in this form. So put this in your notes so you'll know how to do it. Again, these numbers will change, but this is the pattern. Now in this example, we're asked to FOIL, and then once we FOIL, put it in this complex number standard form, and we always keep in mind that I squared equals a negative 1. So we never leave an I squared in the expression. So foiling this now, that's 49. My outers are a negative 21i. My inners, a negative 56. And my last are a positive 24 I squared. But we said I squared is a negative 21. I'm sorry, I squared is a negative 1. All right, thinking ahead here a little bit. So this, we're going to get rid of the I squared here and the positive sign and make this a negative 24. So now we collect like terms. So this leaves us then, once we subtract 24 from 49 at 25, group these together, oh I forgot the I there, a negative 77i, and this is in the form of a plus bi, that is standard form of the complex numbers. In this last example, we're asked to divide this. It's a form of sort of rationalizing the denominator here. So what would we multiply this denominator by to, in a sense, convert it from an imaginary number to a real number? And the answer is its complex conjugate. So the conjugate of this is 5 plus 2i. And the numerator then, 5 plus 2i. Now remember, anything divided by itself except 0 is a 1. So we're allowed to do this. So then we distribute here, and we get 30i. And we multiply this, and we get plus 12i squared. But what did we say I squared was? A negative 1. So we just change this to a negative 12. So that's my top. Now when we FOIL this, the middle terms, since we're multiplying conjugates, cancel out. And this will be 25 minus 4i squared. But what did we say I squared was? A negative 1. So this is going to become a positive. And we can erase the I squared. Now, we are asked to put this in standard form. A plus bi. And the way we do it, this is going to be a 29 here. And this will be a 29 there as our denominator. And this is going to be a negative 12. And this is going to be plus 30i. Or we can put the I out here, it's better. Okay? So again, we did some of these because I know the numbers are going to change. And I am giving you the strategy to get the answers. And good luck on this. Just 20 minutes. And for good measure, let's put the I out there instead of up there. That's okay, but maybe this is better. And I'll give myself a pat on the back. Got 100 on this one. Sometimes I make these little errors.